Welcome to Fundamentals of Artificial Intelligence. We are looking at knowledge representation and reasoning. And in the last class, we have discussed propositional logic. Propositional logic deals with propositions, complete statements used as a whole, their truth values, and logical reasoning involving these propositions. Propositional logic commits only to the existence of facts, but the world being represented may not be so. We have objects, their properties, relationship between objects, and generalization. Those are to be dealt with. Therefore, a language which is more expressive than propositional logic is required. Today, we would look at first order logic, also called predicate logic or first order predicate calculus, a language co-opted by the artificial intelligence community for knowledge representation purposes. A machine that aspires to be intelligent need to somehow formalize the knowledge of the world in which it inhabits. A language for this is the first order logic. The first order logic is our language of choice because it's simple and convenient to begin with, and we have seen that propositional logic is a weak language. Any language that needs to formulate knowledge of the world need to deal with three things that are of our concern here. Number one, syntax. We need to specify which group of symbols arranged in what way are to be considered legal or well-formed expressions within that language. The next is semantics, which is about associating meaning to these well-formed expressions. And then we have pragmatics, which is specifying how the meaningful expressions are to be used. Now, syntax and semantics is easy to understand. Let us take an example to understand pragmatics. In English, the statement, "there is someone behind you," would be a warning or a request. And depending on the scenario, one would become cautious or one would make way. Similarly, in knowledge representation and reasoning, when we say pragmatics, we are interested in figuring out how to use the meaningful sentences as part of a knowledge base from which inferences are to be drawn. First order logic is a logical system for reasoning about properties of objects. First order logic actually augments propositional logic, and it adds predicates that describes properties of objects, functions that maps objects to another object, quantifiers to reason about multiple objects simultaneously. It is these quantifiers that makes first order logic more expressive than propositional logic. First order logic models the world in terms of objects, which are things with individual identities. It is important to realize that the concept of object is very broad. Objects can be as concrete as a person or as abstract as the notion of justice. Objects can be primitive or composite, such as an electric circuit being made up of smaller circuits. Then we have properties which distinguish objects from other objects, relations define between set of objects, and function, which is a subset of relation, is returning a value for a given input. Now, A relation takes objects as arguments and generate a truth value, whereas functions are applied to arguments and then they name things. We will come back to these when we are talking of converting English to first order languages. Let us now quickly look at propositional logic and try to understand what is it that makes first order logic different. In propositional logic, each variable represents a proposition which is either true or false, and we apply connectives to propositions directly. The truth of a statement in propositional logic can be determined from the truth values for the input propositions. That is, one can see all possible truth values for a statement by checking all possible truth assignment to its variables. On the contrary, each variable in first order logic refers to some object in a set called the domain of discourse. The first order variable actually refers to arbitrary objects, and it makes no sense to apply connectives directly to them. In fact, first order logic uses predicates to reason about objects. Like in English, the predicate is part of the sentence that tells you something about the subject. Here, in first order logic, a predicate is a property that a variable or a finite collection of variables can have. Predicates can take any number of arguments, and each predicate but must have a fixed number of arguments called its arity. Here the predicate P x1 to xn is a predicate of n variables or n arguments. A predicate becomes a proposition when specific values are assigned to the variables. That is, when I apply a predicate to arguments, it produces a proposition which is then either true or false. Let us look at a couple of predicates to understand the same. Here is an English statement saying, C is a student at IIT Guwahati. We could have a predicate P x comma IIT to mean X is a student at IIT Guwahati, in which case this X is the only variable that specifies that it is a student at IIT Guwahati. We could also have a predicate P x comma Y to say that X is a student at Y. Here is another example. He lives in the city. We could have a predicate P x comma Y to state X lives in Y. Now, if I instantiate X to Mohan and Y to Guwahati, then here I have P Mohan comma Guwahati, which is a proposition to mean Mohan lives in Guwahati. The domain or universe or the universe of discourse for a predicate variable is the set of values that may be assigned to the variable. And the truth set of a predicate given a domain U is the set of all elements T of U such that the predicate PT is true. Let us try to understand this with an example. Here I have a domain U which is the first 10 integers 1 to 10. I have a predicate P of x which is saying x is even. Given the predicate Px, the truth set is therefore the set of even integers which is 2, 4, 6, 8 and 10. Now let us look at what we mean by function in first order logic. A function returns objects associated with other objects. Functions can take any number of arguments, but each function would have a fixed number of arguments called its arity. Here I have a function of n variables or n arguments. Unlike predicates that evaluate to propositions, functions evaluate to objects when specific values are assigned to the variable. Let us say I have a function mother of x with the meaning that it returns the mother of the variable x. Now, under a common interpretation, which should not be very difficult to see, if I say mother of Jesus, that would return me Mary. Now, let us quickly look at what are the types of symbols we have in first order logic. First order logic has two types of symbols, as you may have made out from our previous discussion. One, it has variables. A variable is any sequence of lowercase alphabet and numeric character in which the first character is lowercase alphabet. Then we have constants. We have three types of constant symbols in first order logic. One, the object constants. The object constant is used to name a specific element of a universe of discourse. We have the function constant, which is used to designate a function on members of the universe of discourse, and we have a relation constant, which is used to name a relation on the universe of discourse. Having introduced a couple of concepts from first order logic, let us now look at what the first order logic provides and what the user provides in order to understand a first order logic representation. The first order logic provides variable symbols. It provides connectives, same as in propositional logic. It provides the quantifiers, the universal and the existential quantifier. The user provides constant symbols, meaning of which is clear under a certain interpretation. The user provides function symbols, and these functions, if you remember, evaluate to objects when the specific values are assigned to the variables. Like here, I could say father of Mary and it could evaluate to John. Or I could have a function symbol like color of the variable being sky and it would return an object blue. The user also provides predicate symbols. The predicate symbols, when instantiated, evaluates to a proposition. So we could have predicates like greater x comma y, and then if I have 5 and 3, then this becomes a proposition, greater 5 comma 3. Here I have a predicate called color x comma y, x is y in color, then I could write things like grass is green because grass is green in color. So a term in first order logic is a constant symbol, a variable symbol, or an n-place function of n terms. A term with no variables is a ground term. In first order logic, facts are stated in form of expressions called sentences or well-formed formulas. So of this, the atomic sentence is an n-place predicate of n terms. A complex sentence is formed from atomic sentences when they are connected by the logical connectives. So we have sentences P and Q, and we could generate not of P, P or Q, P and Q, P implies Q, if and only if Q. A quantified sentence adds quantifiers for all, and there exist the universally quantified sentence and the existentially quantified sentence. Quantified sentences provide a more flexible way of talking about objects in the universe of discourse. Finally, a well-formed formula in first order logic is a sentence containing no free variable. That is, all variables are bound by universal or existential quantifiers. Let us now quickly look at a very special predicate in first order logic. That's the predicate of equality. The predicate of equality states whether two objects are equal to one another. Example here could be, I could have an object TWO2 and an object 2 there, and I could say TWO is equal to 2. Equality symbol is a logical constant and can be best understood as the identity relation. First order logic without equality is also possible, but it is a weaker version of first order logic that has no distinguished equality symbol. Equality can only be applied to objects. If I am talking of propositions, then I need to use biconditional. So, not equal to, given the equality symbol, could be defined as negation of x equal to y. Let us now look at the quantifiers more closely. The biggest change from propositional logic to first order logic is the use of quantifiers. It is the quantifiers that make first order logic more expressive than propositional logic, and a quantifier is a statement that expresses that some property is true for some or all of the choices that could be made. So, it turns predicates into propositions by assigning values to all the variables. So, here is a predicate p of x to mean x is even, and if I instantiate x to 6, then I have a proposition p of 6. 6 is a even number. The other way to turn a predicate into a proposition is to add a quantifier like all or some that indicates the number of values for which the predicate is true. A formula that contains variables is not simply true or false unless each of these variables is bound by a quantifier, and that is what these quantifiers are used for. We will first look at the universal quantifier. The symbol for all is the universal quantifier. The universal quantification of Px means Px for all values of x in the universe, which in the logical notation could be written as for all x Px, or sometimes for all x in D, where D is the domain of discourse, P of x. A statement of the form for all x Px asserts that for every choice of x in our domain, Px is true. For example, we could say all professors are people by saying for all x, if x is a professor, then he is a people. The counter example for all x Px is any t in the domain of discourse such that P of t is false. Let us look at this example to understand what we mean by the counter example for all x Px. For all x, y, z, let some x, y, z refer to z being the sum of x and y. Now, if I take the universe of discourse as the non-negative integers, proposition 1, 7, 8 is true, whereas 5, 1, 8 is false. Let us now look at the existential quantifier. The symbol there exists is the existential quantifier. The existential quantification of P of x is the statement that P of x for some value of x in the universe, which is written as there exists x P of x. A statement of the form there exists x P of x asserts that for some choice of x in our domain, P of x is true. For example, we could say even and prime in the number series, that is the number 2, we could say there exists even x and prime x. There exists a number which is even and prime. A variable can occur as a term in a sentence without an enclosing quantifier. When used in this way, the variable is said to be free. All variables in a predicate must be bound to turn a predicate into a proposition. We bind a variable by assigning it a value or quantifying it. Variables which are not bound are called free variables. If a sentence has no free variable, it is called a closed sentence. If it has neither free nor bound variables, it is called a ground sentence. So, let us now look at translating a couple of English statements to first order logic. Here is our first example. All students are smart. A universal quantifier needs to be used here because we are talking of all the students. But then if we write for all x, student x and smart x, this is an incorrect translation. This is because our translation should work for any choice of x, including things that aren't student. So, if we take certain x which is not a student, this statement fails. Although the original statement is true, this logical statement would be false. It is therefore not a correct translation. A correct translation would be for all x, if x is a student, then he is smart. One needs to remember that a universal quantification is a type of quantifier, a logical constant which is to be interpreted as given any or for all, and this statement will work for any x. Let us take another example, and here we are saying there is a student who is smart. Now, we are talking of existence of a student, and therefore, one thing is clear that we would be using an existential quantifier. But if we say there is a student x, that would mean that he is smart. This would be an incorrect translation. The original statement is false, whereas this logical statement for any interpretation that I take where it is not a student would become true. Therefore, it is not a correct translation. A correct translation would be there exists an x, student x and smart x. Two things that have come to focus in this examples is, number one, if I have a statement that says all p's are q's, then the translation should be for all x, if px then qx. And if I have a statement that says some p's are q's, then I need to translate it as there exists x, px and qx. So, when I look at this statement all p's are q's, this for all quantifier I need to remember is usually to be paired with an implies. In case of the for all quantifier, the implication connective prevents the statement from being false when speaking about some object you do not care about. Whereas, when you are talking about the existential quantifier is to be paired with a conjunction. In case of the existential quantifier, the and connective prevents the statement from being true when speaking about some object you do not care about. And this is something that is a pitfall on conversion of English to first order logic that needs to be avoided. Now, let us quickly look at De Morgan's laws for quantifiers. The first one states that not for all x px is equivalent to there exists not of px. Now, How do you go about checking this? Let's argue it out. If not of for all x px, then we could see that px is not true for every x. When px is not true for every x, I would have some value a where pa is not true. What this would mean is that not pa is true. Since not pa is true, it is certainly the case that there is some value of x that makes not px true, and that is what has been written, that there is an x where not of px is true. We can proceed along the similar lines and argue that not there exists x px is equivalent to for all x not of px. Now let's look at a very vital point in first order logic, that's about nesting quantifiers. For predicate px, switching the order of universal quantifiers does not change the meaning. If I have a statement like for all x, for all y p of x, y, I could very well write it as for all y, for all x, p of x, y. Similarly, one can switch the order of existential quantifiers, like there exists x, there exists y, p of x comma y. This would be the same as there exists y, there exists x, p of x comma y. So I could switch this for all x, for all y, and I would still have the same meaning. Similarly, I could switch the existential quantifiers and I could have the same meaning. But one needs to remember that one cannot interchange the position of for all and there exist like this. So let's look at an example and try to understand that. Here is our third English statement which says everyone loves someone else. So in this statement we can make out that the correct translation would be, if I was just saying everyone loves someone, it would be that I would take for all x to mean everyone and there exists a y to mean there is someone and x loves y. Here, in order to take the fact into consideration that we are saying loves someone else, I would have to include a statement to somewhere which says that x and y are not the same ones. So I take person x to mean x is a person. I take a predicate loves x comma y to mean x loves y, and then I could write a statement here like this, that for all x, if x is a person, it would imply that there is a y where y is a person and x is not equal to y and x loves y. So here in this statement I would have for every person I would have someone who is different from him and they love each other. Now here the order of the quantifier is the universal first followed by the existential. Let us look at a very close statement but hugely different in first order logic. Someone everyone else loves. So correct translation would be there is someone everyone else loves. So this I would again use the same predicate, x is a person and x loves y. I would thereafter write that there is a person x. So first there would be someone and then for all y there would be everyone, and the someone is different from everyone, and everyone loves that someone. So order of quantifier is important when mixing existential and universal quantifiers. For all x there exists y, p of xy would mean for any choice x there is some y where p of xy is true. Whereas there exists x for all y, p of xy would mean there is some x where for any choice of y we get that p of xy is true. Now in here, in the second statement, the inner part has to work for any choice of y, and this places a lot of constraints on what x can be. Now let us look at how we negate quantified sentences. So first we will look at negation of a universal statement. If I give you a statement like all dogs bark and I want you to negate it, the immediate statement that comes to mind is no dogs bark, but that's an incorrect negation. The correct negation for this statement would be that there is some dog that do not bark. All dogs bark. If at least one dog does not bark, then the original statement is false. And therefore the negation would be that some dogs do not bark. We do not want all the dogs not to bark. The negation of a universal statement is logically equivalent to an existential statement with only the phi being replaced by not of phi. So here we had all dogs bark, we replaced it by saying some dogs do not bark. Now let's look at negation of an existential statement. Some snowflakes are the same. Immediately an incorrect negation comes to mind. Some snowflakes are different. But the correct negation would be that no snowflakes are the same. Because here it's saying some of them are same. In order for that to be false, all of them need to be actually different. So we will say all snowflakes are different. So the negation of an existential statement, there exists x, is logically equivalent to a universal statement with the phi being replaced by a not of phi. So here we had some snowflakes, we replaced it by for all snowflakes, and we said same, not of same, we have loosely written as different. So we could write it as all snowflakes are not same. Now let's look at how we could do it for complex statements. But negation for complex statements would mean pushing the not across. So let's look at this statement, everyone loves someone. So here is a statement which says everyone loves someone because I have everyone and there is someone whom everyone loves. I want to negate this statement. So what is the negation of this statement? The correct negation of this statement would be that not for all x there exists y loves x comma y. And then I could push the not forward by looking at the De Morgan's law that we have little while ago tried to argue, that for all x p of x is same as there exists x not p of x. So we could write this and push this not inside, or I could now replace this statement as there exists x not of there exists y loves x comma y. And then I could take this one step forward to replace it with the second De Morgan's law that we had seen, that not of there exists x p of x is same as for all x not p of x, and replace this here to write for all y not loves x comma y. So the negation of this statement therefore would be that there is someone who does not love anyone. So even if everyone loves someone, you want to negate, and the immediate statement that comes to my mind is everyone doesn't love someone. Actually, the correct negation is there is someone who does not love anyone. Now let us look at negation of a universal conditional statement. That is a statement that's conditional but has a universal quantifier in its. So negation of a conditional statement is logically equivalent to an AND statement. That's what we have looked in propositional logic. Not of P implies Q is same as P and not Q. We could look at this way. Not of P implies Q. So P implies Q I could write as not P or Q. And then when I have a not of a disjunction, it is not of the first and not of the second. So I have not of P and not of Q. So double negation, I end up having P and not of Q. So negation of a if-then statement is logically equivalent to an AND statement. And then we have seen that negation of a universal statement is logically equivalent to an existential statement. That is, not of for all x phi is same as there exists x not phi. Now substituting the conditional statement into the universal statement here, we would have not for all x px implies qx. That's the conditional statement, which is universal conditional statement. The negation of the universal conditional statement is same as saying there exists x, px and not qx. Let's take an example and try to understand this. If x is a rational number, then root of x is a rational number. How do you negate this statement? Now first you need to realize that this is some form of an universal statement, because it is saying that for all x which are rational, then it is saying root x is rational. So what is the correct negation? For the correct negation, I need to realize that I can introduce the existential. There exists x which is rational and root x is not rational. So the correct negation of this statement, if x is a rational number, then root x is a rational number, is the statement saying there exists a rational number x such that root of x is not a rational number. Now let us look at the distributivity of our universal quantifier over a conjunction. So for all x px and for all x qx, this is same as for all x px and qx. That is, that for all distributes over end. No matter what the domain is, these two propositions always have the same truth value. Now this should not be surprising. We can argue it for a finite domain. Say I have my domain of discourse being the digits 1, 2 and 3. Then when I say for all x px, I could write it as pi and p2 and p3. And for all x qx, I could do similar thing. Further, and is commutative and associative. So I could write for all x in the domain 1, 2, 3, px and qx could be written as p1 and q1 and p2 and q2 and p3 and q3 for this example domain. I could then bring the p's together and the Q's together because of AND being commutative and associative, and end up having for all x in the domain 1, 2, 3 px, and for all x in the domain 1, 2, 3 qx for this specific example. Though this is only an example domain, the intuition extends to other domains as well, including infinite domains, and we can say that the existential quantifier distributes over the AND connective. Now let's look at distributing the existential quantifier over AND. There exist x, px and qx not equivalent to there exist x, px and there exist x, qx. What it means is that the existential quantifier does not distribute over the AND. We need to find a counterexample, a universe and predicates P and Q, such that one of the propositions is true and the other is false. Then literally we would have shown this. So let's take U to be the set of numbers, x is prime and qx is composite, that is not prime. Then there exists a number which is prime and composite is false, whereas I could definitely have a prime number and a composite number, and this is true. So if you look at the distributivity of the existential quantifier over the disjunction, we see that on the contrary, the existential quantifier distributes over the disjunction. So recall that for all x, p of x and qx, we had shown that for all x it's px and for all x qx. Now this statement here holds for arbitrary p's and q's. Therefore, let us take p to be not s and q to be not r and replace them in this formula. So we have for all x not of sx and not of rx, and this side also we replace p by not of s and q by not of r, and now we negate both sides. So here when we negate for all x, when we negate, we will introduce an existential quantifier which says that there exists not of whole of this expression here, and this side the negation being applied to a conjunction, we will have the negation of the first part or the negation of the second part. So we will then take the negation inside here and we will have the negation of the first part or the negation of the second part. So these two negations will give me an s. Here I would end up with an r, and therefore finally I will have this statement which is saying that there exists x, sx or rx, there exists x, sx or there exists x, rx. That is, there exists distributes over the disjunction. So we have seen some fundamental concepts in first order logic in our lecture today. We will continue this discussion in our next lecture. Thank you very much.